for the COVID-19 analysis and projections activity, you're going to be actually making some projections of your own. I'm not going to read all of this, but I'll maybe highlight some things. But many projections have been made regarding the spread of this virus, and you've undoubtedly seen many of these projections in the news. Mathematical models are being used for these projections, and accurate models are essential to knowing the resources that you're going to need, such as medical personnel, facilities, masks, gloves, ventilators, and all of that type of thing. The more variables there are, the harder it is to predict. That's why you see so many various different projections out there, some way larger than others. So let's talk about the spread of disease, actually. This is something that's important to understand. Diseases tend to spread based on a logistic curve. At first, when the disease spreads, it might look exponential, and early on, it is basically exponential, and that still seems to be what we're kind of seeing in the United States right now. This will eventually, however, trend away from exponential and more toward logistic, meaning it's going to approach a horizontal asymptote. To compare the two shapes of the curves, you've already seen the video, but let me show you over here in Desmos. So here you have an exponential function. I just graphed 2 to the x. It has a shape something like this. It just keeps growing and growing and growing. Obviously, there's a limit to how many people can even be sick because your population is not infinite. So what's going to happen eventually, as more and more people have gotten sick and recovered and it's spreading, it's going to kind of run its course, it's going to approach more of a logistic shape. Now, early on, an exponential function and a logistic function look very similar. For instance, this would be a logistic function. You can hardly see any difference at this point in the graph. But if I start to zoom out, you'll see the red and the blue start to separate, the blue being the logistic. And in fact, let me just shrink down the y-axis a little bit here. Like, let's let the y only go to 100. Yeah, let's make it a little bit more than that. Let's make it 500. So we can really see how they start to branch away. So you can see the exponential keeps growing exponentially. That's the red curve. The blue curve is logistic. It's approaching an upper bound. That upper bound it's approaching, if you're talking about the spread of disease, would be the maximum number of people you expect to eventually get the disease, the illness. Over here from these graphs, you can see the red graph is that of 2 to the x. The blue graph is that of this logistic function. The numerator of the logistic function gives you that upper bound that it's going to be approaching eventually. All right, so with that in mind, let me go back over to the sheet. Down below, this is a graph from the CDC. Representing the total number of known cases of COVID-19 in the United States. It goes from January 22nd, where the first known case was identified, up through March 29th of 2020. You can see early on the cases are so small you can't even see them on this scale of the graph. It really doesn't start to take off until around maybe right here is kind of the starting point. And so that's the date we'll emphasize as time 0. It's actually going to be March 12th I'm going to use as time 0. That would be exactly 50 days after the initial case was identified. And then from that point you can see it does appear to be growing exponentially along this curve. Well, what you're going to do in this activity is open your web test in Hawks. It goes right along with these sheets. You'll print these pages that I'm going through right here. And then also open the web test that goes along with it. The first step is to find an exponential function that best fits the CDC data shown in the graph on that previous page. In Hawks, there's a Desmos link to the CDC graph along with an interactive exponential function. You are to manipulate the parameters of this function until your curve seems to fit the graph well. And then a note, keep Desmos open during this entire problem because you're going to work with Desmos some more in step 2, and then later on as well you're going to provide a link to it. So, and then enter your function into your Hawks web test. Let me show you what that graph looks like. When you open it up from Hawks into Desmos, it'll take you to this. There's that CDC graph you just saw. You can zoom in on it. You can zoom out. As I was talking about, there's hardly any data at all until you get to about day 50. You can see that day 50 is right here. That would correspond to March 12th. March 11th is this data value right here, which is day 49. March 12th is day 50 here. So I've modified the function. If you look over here, you see t minus 50. That's shifting the graph 50 units to the right. And so this is my new ground zero, basically, at March 12th. And so that's what that does to that standard exponential function. Same thing with the logistic function down here. You have that one that can be manipulated as well. It's going to start with t equal 50 representing day zero, basically, on this. But to make it work that way, I had to replace t with t minus 50 here, and that way it's going to be 50 is kind of corresponding to 0 on this, even though day 0 on this graph is January 22nd. Go back over here. January 22nd is technically day 0. My shifted graph is what I'm talking about. So anyway, that's how these functions are going to be modified, by manipulating these variables. So if I click on this, you can see there's my original exponential graph. It doesn't seem to fit it very well at all yet. But by manipulating, there's only two constants here, the p and the r. By manipulating those, you can adjust the graph. All you have to do is scroll, pull it left and right to manipulate those values. So p will be basically your population at time 0, or time 50 in this case. And then the r represents the rate at which you're growing. And so you're just messing around until you can get that. You can see eventually you're going to be able to fit it nicely to this curve, relatively nicely. Now again, this is an exponential function, and like I've said, even though early on it appears to be growing somewhat exponentially, it's not going to continue to grow exponentially. Eventually it's going to start to die out and approach that horizontal asymptote. So if I go back over to the sheet here, you can see the second step then is to find a logistic function that best fits the CDC data shown in the graph, just like you did with the exponential, using Desmos again. And then once again, you'll enter that function that you arrive at in Hawks. I expect everybody's answers to differ a little bit because everybody's just scrolling and manipulating these values until they get something they think fits it very nicely. And then you just enter the function. So if I thought this fit it nicely, which is not horrible but not really good there, I would say my function then is 3,970 e raised to the 0.199 times t minus 50, and that is what I would enter in Hawks. Logistic, you can see, is going to fit it a little bit better, but now there's three things to manipulate. The m, and again, remember the numerator is going to represent the maximum number of people to eventually become infected with COVID-19. And then there's a c, and there's also a k. K dealing with the rate at which it's growing, and c is another constant in there that you need to find to fit the data very well. So I can see I can manipulate the maximum that there's going to be. I can manipulate the c, and you can see how that's changing the graph as you manipulate that. And I can manipulate the k. And so you can see where that's taking that logistic curve. And you're wanting to fit that to this data. So it shouldn't take too long. You manipulate those. The window's given there too. You just manipulate it until it seems to fit that graph really, really well. Once you get that, enter your functions. You're going to have to type a function that looks just like this. Just fill in what your m and c and k values are for that function. When you're done with that, you're going to use your function to make some projections. It says use your models to predict the number of infections in the United States on May 1st, June 1st, and July 1st. And so here's where you can show your work as to how you're calculating that. Just use your calculator, get those calculations for both the exponential projection and for the logistic projection. And once you've calculated all those values, you're going to see quite a bit of difference. Maybe May 1st might not be as different for the two, but you should see further and further separation. And then steps 4, 5, and 6 will be questions, just interpreting your answers. Provide your answers in Hawks. Just type those answers in. You can show any associated work for anything down here. There's not a whole lot of work there. It's mainly just making sure you kind of understand what you found. Again, just to kind of give you a little better feel and understanding as to what's going on with the spread of this virus, and understanding how they can calculate such projections. And you're going to compare your projections with those that are being done in Washington. And so that's the assignment there. Complete that web test, and then when you get done, you will also submit your worksheets to me by scanning them and posting them in Canvas as you've done before. So I think that pretty much covers it for the COVID-19 analysis and projections. Be sure to email me if you have any questions on this.